Hello.
Hey, how are you?
I'm good. How are you?
I'm good. So I see your score went up
By a point, yes, yes, yes.
in CP, which is good because I'm pretty sure last time that's what we went over, right? CP stuff.
Yeah, CP's been a little hard. I got the, what do you call it? The question banks for like the volume two. I saw that it's like new for 2025, so I got that and I've been like working through it. My goal is to kind of like do all 100 questions like for each section by my next practice test on Sunday. So,
You're talking
yeah.
about section banks?
Yeah.
Okay. Because there's like question packs and then there's a section banks. So the section banks are the ones where there's a volume one, volume two for, each of the sections. So, yeah, good stuff. You're now like consistently, past 500. So, yeah, really good
I'm
stuff.
happy about that. I'm like, I don't know if it's the real, like possible, but my friend, she had a 7 point jump on her test day. I mean, granted, she was already like super high and she's like a AP Bio, AP Chem teacher. So she was like at a 512 whole entire time and just jumped to a 519. So like great for her. But
Mhm.
I'm just like, ooh, if I could just jump to like a 509, 510, I would be super happy.
Yep. Yeah, that's the reason that I have, you do like the blueprint or Altius tests and stuff, uh,
Yeah.
which suck when you're actually doing it and, and also could be discouraging with the deflated scores, but they are deflated. So now, now you see how the AAMC ones are, you get your boost. So awesome, awesome. So were you able to like blind review and review it yet?
Yeah, I did. Well, I did. I'm like going section by section. Like, I don't know if this is good or if I should just. I did the blind review for the Chem Phys section, and then I was just like taking notes on everything that I got wrong, and
Mhm.
then I was doing the. I started the question bank for the section bank for the Chem Phys section because I'm almost done with the question packs for chemistry and physics. So I was like, let me do the section banks. But I haven't done the bio blind review yet. I was planning on doing that one like either later tonight or tomorrow.
All right. Cool, cool, cool. All right. What would you like to work on today?
Um, I feel like I mean because I'm like we're always doing Chem Phys, but it's just my lowest section for sciences right now, and like my goal is to get like the Chem Phys to like a 127
Yep.
at least, just because I don't know, I feel like that's what the schools are looking for. I
Yeah.
was like so nervous because my friend was like, "Oh, like if you pushed it back to July, like it would make sense." But I don't know. I feel like with this application cycle, like I don't know if I don't necessarily. I think that I could get it together. I have 10 days. I mean, I took a half day at work today. I think I'm gonna take sick days at work just because I'm like it's so stressful and
Yeah.
um
Yeah, definitely for for these last like weeks, because your test is on the 28th, right?
mhm.
And you're gonna be doing your next full length sometime like what, this weekend, Saturday?
Yeah, or a Sunday.
Okay. Um, yeah, yeah. Totally, take these like this and next week off so you can focus on this. But yeah, it's totally doable. Um, and yeah, I think you could totally pull it off in time for your application and everything. So yeah, what would you like to go over?
Okay, good. Oh
Mm-hmm.
well. Like I'm so stressed out like these last few days. But I finally feel fine, but I was so stressed.
Mm-hmm.
So I feel like I figured out the things from the Chem Phys like
Okay.
section of my exam, but I was looking at the section bank like that was what I was working on today and I had questions on that. So I was like, let's just
Got it. Volume one.
volume two.
Oh, you already finished volume one?
I was just doing, I didn't get volume one just because like someone, well, I was looking at like Reddit and they were saying that volume two is like the most up to date one. Is there like a big difference between volume one and two? Wait, no, it's not it.
I would say that they're both super important to get. Um, because you're not doing like the Q packs, right? Like I think we talked about those. Like if you hit this, let me see what comes down.
Yeah, I have the Q packs.
Yeah, so don't do these Q packs because they're from the old test.
Oh, okay.
Yeah. The only Q packs that are relevant will be the cars Q packs because that section hasn't changed from the old MCAT. But like these bio Q packs, chem Q pack, physics Q pack, they're from the old MCAT, so they're not going to be that relevant. But so like the time that you were planning to spend on those Q packs, you could spend on the section bank volume one, I would say. I would say that the volume one, like, yeah, both of them I would say are like, probably like some of the most important stuff from the AMC. Yeah, no, I would say actually that they're the most important stuff from the AMC other than the practice tests. So I would definitely get um the volume one as well.
Okay, gotcha. Gotcha. Okay. So this here, I feel like I did okay on this, but there was still some things that I wasn't understanding, but I think I'll get that one together. I feel like I was getting things wrong just because I wasn't understanding like the way that they were asking the question.
Hmm. Yeah,
Um,
that's section make volume two is definitely like on the weird side. Um in terms of like the way that in terms of what they ask you and in terms of what they expect you to know, like there's some really like weird like minutia that comes up that is definitely, you know, weird compared to all the other material. Um yeah.
okay, yeah. So I was thinking we could go over this passage and then the passage after this one.
Mhm.
Um, I'm like, should I use the jack? I probably use the
Yeah.
jack. No, oh, wait, no. It's fabric. Okay, yeah, this passage.
Yeah, and also like what you're saying about wanting to focus on the CP section, like that's like the second, so like in terms of difficulty as far as, percentiles are concerned, um from lowest to highest difficulty, the order is Psych Soc, EB, CP, and then Cars, meaning Cars has the lowest average score, followed
Okay.
by CP, followed by BB, followed by Psych Soc. So it makes sense what you're saying, like, you want to focus on on CP. Because yeah, like they do like to see that. Um and yeah, okay. So you can do
Yeah, it's just because I have like a 125 in it, and I'm like, I don't know. I'm like, if even if I get like a 126 on the test day and I'm able to like pull, because I definitely feel like I could pull my biochem score up and my psych soc score up just because there's like certain things that I haven't memorized for it yet.
yeah.
And so I'm like, oh, if I get like a 126 in chem phys, that's okay. I mean, I'm not like aiming low. I'm just feeling like the way that chem phys has just been going has been like so slightly discouraging for me.
Yep. Yeah.
But who knows? Maybe I'll get it together. So should I read this passage?
Yep. And when you come across, any buzzword or anything like that, let me know, and I'll also like kind of interject and ask you stuff about some of these concepts. Um, but yeah, go for it.
Okay. Researchers studied the occurrence of cardiovascular injury in patients exposed repeatedly to therapeutic electromagnetic radiation in the form of high energy X-rays of frequency 1.5 times 10 to the 17th hertz.
What's electromagnetic radiation?
Um, like a wavelength.
Oh, what?
Yeah, I feel like it gives off wavelengths of like
Well, wavelength will be the length of a wave, which could be for any type of wave. Like you'll always have a wavelength, but so electromagnetic radiation. So it's kind of weird because when people, um, like regular people think of the word radiation, they think it's like something that's, going to give you cancer or whatever. But it really just means that something is radiating or kind of getting emitted. And electromagnetic radiation is just light. And it's called that because light, like, if this is the direction of a moving um, photon, like this pen, perpendicular to the pen, perpendicular to the direction that the photon is moving will be an electric field. And then perpendicular to the electric field and the direction the photon's moving in 3 dimensions is a magnetic field. So, um, let me put a in the chat. So yeah, see if you could open that up and share. Yeah. So,
wait, it's not moving. Oh, that's okay? Doesn't need to move.
um, you could like show the chat. Um, and maybe that will
You see it?
no, but
Okay. Wait, hold on.
okay.
Can I share the chat? I always feel like a boomer when I'm on here sometimes. It's like I don't know the zoom in and out.
Well, is it moving for you?
Yeah, I could see it.
Okay, so basically what you see there is you see the x-axis is the direction that the photon is moving. I mean, you can't really see the foot like there's no like, drawing of the photon, but let's say that it's moving down that x-axis. It makes perpendicular to that along the y-axis that blue wave. So that blue is, yeah, and you see how it says capital E.
Yes.
So that blue is the electric field, and on the z-axis, you can see the red capital B, and that is the magnetic field. So what this basically is showing is that any movement of a photon, which is just a particle of light, produces both an electric field and a magnetic field, and they are all perpendicular to one another. And
Gotcha.
so a moving charge could also do this, which meaning a moving charge could also produce like a magnetic field, but a photon will always produce a magnetic field and that electric field, and that's why electromagnetic radiation is just a like fancy way to say light. So like right now, are you experiencing electromagnetic radiation?
Yeah.
Yep.
Yeah.
So, but like, when people think that, they're like, oh no, it's like bad, like, but light is just, electromagnetic radiation. So when you see that, just think light. And know that light, you know, produces a magnetic field as well as an electric field, and that they're all perpendicular to each other.
Gotcha.
All right. And then it says high energy X-rays. Um so let's say compared to visible light, tell me like an X-ray's energy level.
Um, Compared to visible light, X-rays have a higher energy level,
All right. And what about frequency?
higher frequency as well.
What about wavelength?
Um, I think it's a smaller wavelength.
All right. Um, and yeah, that's because they're like inversely proportional. Now, if you're given the frequency of this X-ray, what else could you solve for if you needed to?
Um, you could solve for the wavelength
All right, how?
by like knowing the speed of light.
Okay. And then what would you do exactly?
So it would be I think it's like 3 times 10 to the eighth. Uh
Yep,
yeah,
what
equals the frequency times the wavelength.
what unit would that be? The 3 times 10 to the eighth?
Um oh wait, yeah, the speed, meters per second.
Good. So so for any wave, the speed of the wave, v, will be equal to the frequency of the wave times the wavelength.
Yeah.
And so wavelength would be in some unit that expresses, oh wait, no, that's not. That expresses length. So that could be like meter, right? And then frequency, we know the unit as hertz, but hertz is another way of saying the number of cycles per second.
Okay, that makes sense.
So let's say, so I drew this wave here, and what would the frequency be here?
Mm, 2.
Good, because you have two cycles, right?
Yeah.
Yeah, like like this is one, and then this is the second, and it happens from 0 seconds to 1 second. So two cycles per second. So yep, that'll be 2 hertz. Good. Um, and so okay, hertz you could think of as cycles per second, but cycles won't have a unit. So hertz could be expressed as 1/seconds.
Gotcha.
So when you multiply 1/seconds by meters, you get meters per second, right?
Yes.
Okay, so that means anytime they give you like a frequency of light or a wavelength of light, you could solve for well, since you know the speed of light and let's say you're given frequency, you can solve for the wavelength. Um, and if you're given wavelength, you could solve for the frequency. Now, what else could you solve for?
Um, from the frequency.
Hmm.
Oh, the energy of the photon.
All right. And how would you do that?
E equals H
Uh-huh.
times F.
Good. And H is what?
6.6 times 10 to the negative 34.
Good, 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 good. Planck's constant. Now, what if you were given wavelength instead of frequency?
Um, and I'm trying to find the energy. Uh, then I would have to plug it back into the V equals
Mhm.
frequency times wavelength, and then find the frequency and then put it into.
So we can then just write for the velocity, I could just write c,
Mhm.
and now what?
Wait for this is when we have the wavelength and we're looking for the frequency.
Oh,
Oh,
you have the wavelength, but you're looking for energy.
oh, okay. So yeah, then you'll find the frequency using C. When you do it's C over the wavelength equals the frequency.
Good.
And then yeah, you put it into E equals HF.
So energy of a photon, so okay, this here is true for all waves, right?
Yeah.
And it just happens that for a light wave, the speed is c, at least in a vacuum. Um, and then the energy of a photon, this is only something that works for light. Like it doesn't work with like a sound wave or anything. So that's Planck's constant times frequency. And if we don't have frequency, but we have wavelength, we could just set frequency equal to c over lambda to get hc over lambda. So I want you to like get into the habit of anytime they give you either a frequency or more likely they'll give you a wavelength of light to know that if you needed to, you could solve, like if they just gave you the wavelength or if they just gave you the frequency, you have everything you need to be able to solve for the energy as well as the, well, if you're given frequency, you can solve for the energy and wavelength. If you're given wavelength, you could solve for the energy and frequency, right?
Yeah.
Okay, good. Continue.
Researchers perform computed tomography CT scans using low energy X-rays of wavelength 10 nanometers in air.
All right. So they're kind of doing what I was saying. Like, so first they talk about high energy X-rays with that frequency. And if we needed to, we could find the wavelength. And then they give us the wavelength of the low energy X-rays. Um, and yeah, if we wanted to make like a direct comparison, we could do that. Um, would you say that the like high energy X-rays that they're talking about, what do you think their wavelength would be greater than 10 nanometers or less?
Less.
Good, because it's higher energy, right?
Mhm.
Good. All right, continue.
The X-rays were collimated by passing through an opening of width D, which is equal to 1 micrometer, and the length L, which is equal to 10 micrometers, made in a copper plate.
Okay, so now collimated is like a way of saying like getting light to move in like a straight line, kind of like a laser.
Okay.
And And then they're telling us that, so let's say we're shooting the light here, and they're saying like the opening that the light comes out of has a width of 1 uh micrometer, right? And a length of 10 micrometers. Um, so okay, if the wavelength is 10 nanometers and the width is 1 micrometer, um, let how can we compare these? Like,
I well, I just feel like the width is big enough for the wavelength to pass through.
uh-huh. And how would you be like how would you verify that?
Well, I mean, because it's like 10 to the -9,
Hmm.
and D is 10 to the -6.
Very good.
Yeah.
So the 1 micrometer is it's like 1,000 or rather 100 times larger, right?
Hmm.
Okay. And um and this kind of connects to the idea of diffraction, which means like, so let's say we have like a slit where the width of the slit is much larger than the wavelength of the light. So if this is a light ray with its wavelength that's smaller than the slit width, it can just go right through. And so light behaves as can behave as a wave as well as a particle. And initially, like, humans, we thought of it as photons or particles, but what this guy Young did back in the day was he experimented and he made it so that the width of the slit is smaller than the wavelength of light. And so if this MetroCard was the light with this length being its wavelength, and let's say this what I'm doing with my hand is the slit. So if the slit's way, larger than the light, it could just go through it and, there's no way to see if it's acting as a wave or not because it just will act like a particle.
Hmm.
But if we make the slit smaller for the wave to, since the light has a longer wavelength than the slit, it's gonna have to, it can't just go through like easily. Like it'll kind of, the center part of the light will go through and it'll bulge kind of like this as it goes through. So here, this is going to be, or let me use a different color. So here, I'm going to draw it here. So, and then I'll use blue. So this is the light ray. And then when it gets here, it's like the center part gets through and the edges, the ends are get through like later. Um, Meaning like the center of the wave goes through faster than the ends. And so by the time, the center of the wave gets all the way here, the ends of the wave, like there's that kind of delay, right? And so this emerges as like this type of pattern, right?
Okay, wait, so just to confirm, because I know you were saying that light could be a wavelength and particles, as it's like trying to move through the slit, is it like turning into particles?
So like let's say, it's like 500 years ago or something like that. we we would think of light as particles, and that would be the case if you had a larger slit width, because then the light can just go right through. And and then like let's say this is a wall, you would see, and let's say the wall, we measure like the intensity of the light that reaches this wall, you should see pretty much something like that, right? But now what Young did was he experimented with making a tiny, tiny slit that's smaller than the wavelength of light, so that when the light rays travel through the slit, only the so like draw. So like let's say again, this is the slit here, and then this is the light ray. So for this to go through this slit, it'll have to kind of bend like this, which means that the center of this goes like first through the slit, and the ends kind of lag behind.
Gotcha.
And so what ended up being seen on the wall that's on this opposite end is something like this. Okay. So now think about, so here in this drawing, where light behaves as a particle, like this is where the light is. And so this is where this peak here is just, I mean, it's like not physically there. It's just
Mhm.
a measure of how much light is at this region.
Yeah.
And so if light is behaving as just a particle here, you should see the light intensity only in that center region, right?
Yeah.
Um, but once we start to have a slit that's smaller than the wavelength, then the center of the light travels first and causes this peak. But the ends here are a bit delayed. And so, but they still reach this wall, which is why you have some peaks, some smaller peaks on the ends here.
Okay, that's pretty cool.
Yep. So like basically before this experiment, uh, we just thought of light as a particle. But once this experiment was done, we were able to see that if you had a particle can't bend like that, right? So that's um like revealing the wave like characteristics of light.
Gotcha. Okay, that makes sense. Because like there's also a question on this in this question set, and I definitely I didn't know what
And
the
like a pinhole camera?
yeah.
That's how that works too,
Oh, that's
right?
cool.
Because like imagine you take a pinhole camera and you just make it, instead of a pinhole, a really big hole, then it's not gonna work, right?
Mhm.
It's just gonna have all the light rays go through. But if you have the pinhole, which is so small, the light that goes through, like like if this is light, like the center of it would go through first, right? So, yep.
So this concept right here, this is just diffraction.
Yeah. Basically, this with the like that, right? like the that type of bending is um diffraction. So you can think about it as when the wavelength of light is longer than the width of the slit that the light can go through.
Gotcha. Okay. The X-rays were absorbed selectively by the irradiated heat heart tissue based on the atomic number of the chemical species present in the scanned area. Okay. X-ray detectors placed a circular pattern around the patient's heart, collected the X-rays, which passed through the tissues. So it's like circular X-rays, okay. Based on the number of X-ray photons collected, each detector generated an electric current with a typical intensity of 15 microamps that
All
was
right.
sent.
Oh yeah. Now, so they're being a little weird here because so intensity is its own like thing, which relates to the number of photons. If it's light, if it's sound, it's like the number of sound waves. Um, and if it's light, the number of photons corresponds with brightness. And if it's sound, the number of sound waves or the intensity corresponds with loudness, right? Um, and the unit for intensity is power over area, so watts over square meters. Now, they are calling current, like they're describing it as an intensity, but it's not really intensity, right? But it's current. So they're being a little weird here. Um, now, so the current is 15 microamps. What can an amp be if you deconstruct the units?
That's coulombs per second.
Very good, very good.
And then I just found out today that you could get like electrons from current.
Well, yeah, because when you have electricity, you have the movement of electrons, right? And an electron uh, has a charge of 1.6 times 10 to the negative 19 coulombs.
Hmm.
So, if we have something that's like, well, like 1 coulomb or 1 amp or whatever would be like a really large number of electrons. But yeah, yeah, pretty much that. And also this circular pattern thing. So like that's how a CT scan works. Basically, a CT scan is just uh X-rays that are taken like well, a ton of X-rays are taken around you, like in a circle, and it creates and it can by making these slices like let's say like it shoots an X-ray here, 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 like the part where the X-ray comes from can rotate in a circle and it just keeps taking these X-rays and each time it makes like a slice. And then if you could and then you can put all the slices of each of the X-rays together to make a three-dimensional image.
Okay.
And that's like that's how like a CT scan uh works. It's basically a three-dimensional X-ray.
Nice.
Hmm.
Um, oh yeah, because it says here, yeah, I'll make a composite image from all the
Yep.
detectors.
Hmm.
The data revealed that calcium coating plaques were formed in the left ventricle of the patient subjected to an absorbed dose per unit time in excess of zero point zero 0.04 gly per second. The 1 unit, I mean gly, I'm bugging, GY or G. The 1 unit of Gui represents 1 joule of radiation energy absorbed by 1 kilogram of absorbent material.
Okay. So how many ions can form? Let's say you have 1 molar of this and this dissociates. How many, like what concentration would you have of the individual things?
Calcium, that there'd be 1 mole of calcium
Mhm.
and is it zero point 0.5 moles of chlorine? I mean,
So what would this break into?
Ca2 plus
Yep.
plus wait, hold on.
Hmm.
Well, yeah, Ca2 plus 2Cl minus.
Good, 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 good. That's just from last time, remember?
Yeah, I know. I've been trying to I've
Mhm.
been working on that because I'm just like I always get tripped up on st
Mhm.
but on it. So yeah, so it would it be zero point 0.5 moles of Cl?
2 moles, because this will break up into 1 molar Ca2 plus two chloride ions,
Hmm.
right? As
So
opposed to one Cl2.
okay.
Mm-hmm. We're
Like the
yeah.
concentration doesn't have to equal 1 molar for the chlorine. I mean, yeah.
So if we start off with 1 molar of this has 1 atom of calcium and 2 atoms of chlorine. So when they break apart, you'll have 1 molar of the calcium, but since you'll have 2 molar or twice the amount of chloride ions, like this will then be 2 molar.
Yeah. Okay. Gotcha.
And so yeah, so far we have all of these things that they could, so like we can make perhaps some predictions of what types of questions they can ask us. Like they'll probably ask us something about, the high energy X-rays compared to the low energy X-rays. They'll probably ask us something about like diffraction, um, with this, slit thing, a copper plate. Maybe they'll ask us something about that, but then they talk about current, so they're probably going to ask us something about, um, how many like electrons per second, or you know, something about a circuit maybe. Um, they might ask us something about calcium, and this is a weird unit.
Yeah, I thought it was so weird. I was trying.
I wonder if it's like Geiger or something.
Oh.
No, it's gray. So, which is the official SI unit for measuring absorbed the absorbed dose of ionizing radiation, and it's equal to, oh yeah, joules per kilograms. So, okay.
Yeah.
And yeah, they'll definitely ask us something about that. So, all right, cool.
Um,
And yep, so here we go.
we're
So
gonna
This is exactly what I was going to, yeah, one of the things I knew that they were going to ask. So, what are they asking us here?
They're asking what the what is the gap between atomic energy levels that correspond to the emission of the therapeutic high X-rays.
So,
Uh,
do you remember when we talked about like a photon being absorbed, causing an electron to be excited, and
mhm,
then when an ex electron relaxes back down to its ground state, it'll emit a photon with that much energy. So so when they're saying the gap between the atomic energy levels, they mean the shells that the excited electron can jump up to, right? Uh,
yes.
so
Okay, that makes sense. I guess I was so confused like when I first looked at this, like I couldn't figure it out, but I realized it was just like the E equals HF. But I guess is it 'cause they said like emission? Is that like a
yeah.
good one?
So let's make sure that we have this down because it's super, super high yield. So let's say that, so this is the nucleus, whatever. This is n is equal to 1, the ground state shell. And let's say this is n is equal to 2, and n is equal to 1, n is equal to 2. So the electrons at the ground state, which is n is equal to 1, and let's say that the energy level between n is equal to 1 and n is equal to 2, let's just say it's 1 electron volt. If I shoot a photon of 0.99 volts at this atom, what would happen?
So I think the electron would move energy shells to make space for the 0.99 volts.
So how much energy is required for an electron to go up a shell?
One electron volt. So actually, I guess it wouldn't move.
What about, would it go up like 99% of the way?
Yeah.
So what if I shot two with this much energy?
Then it would go into the n equals 2 shell.
So So if you just take so why do they even need to use these X-rays? Why don't they just use a flashlight and just shine it on something for a really long time?
Um, because the X-rays have like a higher frequency.
So which would mean that they have a higher energy, but why don't they just take something that has smaller energy and they and just shoot more of them?
Because you wouldn't be able to see anything.
So so in actuality, these photons won't do anything.
Okay. Wait,
So
there's like more than one of them. 'Cause there's two.
yeah, so this is super, super important concept. So this is quantum mechanics, and it's called quantum mechanics because a quanta or a quantity is a discrete like amount of energy that is stepwise with nothing in between. Well, what I mean by nothing in between is so So if you have 0.99, if you have a photon with 0.99 electron volts, but you need 1 electron volt, it's
Mhm.
not going to bring it up 99% of the way. It's not going to bring it up any percent of the way. It's not going to be absorbed because it doesn't have enough energy to be absorbed because quantum mechanics requires exact energy levels, nothing in between.
Oh, that's cool.
Yeah. So now what they like to ask is like if this zero point 0.9 electron volt photon is not absorbed, what they like to ask is what if you increased its intensity? And
Which is
so, yep.
over power over area, right?
So intensity has units of power over area, but what did I say intensity was?
Watts over, um, is it meters squared or
So those are the units, but what so but what would intensity like actually be? So it'll be the for light at least, the number of like think of it as like the number of photons. And if you have and that corresponds to brightness, but and like write it in red or whatever to make sure it's not energy.
okay.
So when I said um like what if we have two of these photons from one, like if I'm adding another photon, I'm really increasing the intensity, right?
Yes.
But am I increasing the energy?
No.
So
No.
it doesn't matter if we have one of these photons, two, or like 2 trillion, none of them will be absorbed.
Gotcha.
So, so yes. So remember that energy is so this is called quantum mechanics because there's discrete energy levels. When I say discrete, do you know what I mean? Like I kind of use like a staircase, like steps in a staircase. Like there's no half, you can't go up half a step, right?
Yeah.
So it has to be like, all or nothing. Um, so yeah, nothing can, and then also since uh the energy of a photon is it's dependent on its frequency. That's why like the energy of a photon or its frequency of a photon does not change. So, so okay, so let me ask you this. So I have red glasses and blue light is coming in, or light in general is coming in and hitting my glasses. Um, and let's say that it blocks out like blue light or something, or let's say any like blue light blocking glasses, like not it doesn't even have to be red. Um, does that mean that when the blue light hits the glasses, it turns into not blue light as it hits your eye?
No.
Why not?
Because like it's still it still has like the same wavelength and the same energy level.
Yep. So, uh, so there's a little weird thing with wavelength could be kind of manipulated, but frequency can't, and
Okay.
energy can't either. So if you have a blue photon, like it's intrinsically blue, like it can't change. It can't turn into a different color or anything like that. So yeah, that won't change. So okay, good. So now if we have a photon with 1 electron volt, that is enough for so that's enough for this photon to be absorbed. And I want you to think of it in a sequence like this. Like if the photon is absorbed, the atom absorbs that energy, and it expresses that increase in energy by exciting an electron from its n is equal to 1 ground state to the n is equal to 2 excited state. So this electron moves to this higher level shell,
Gotcha.
and that's how the atom deals with an increase in energy. And when the electron moves back to the ground state, it must, since it's going down in energy level, the atom itself has to lose that energy, and it does so by emitting a photon with 1 electron volt of energy. And so the sequence is like this. So if you have a photon that's absorbed by the atom, an electron will be excited to a higher energy level. And if that electron relaxes back down to the ground state, it'll emit a photon with that same energy level. So absorption of a photon can cause excitation of an electron, but in order for a photon to be emitted, the electron has to go relax back down to its ground state.
And is that just happens with time?
Oh, you mean going back to its relaxed state?
Yes.
Yep. Because anything that is higher in energy is lower in stability.
Gotcha.
And that actually leads me to the other scenario, which comes up a lot, which is fluorescence. And that's when you have a molecule with a lot of conjugation, aka resonance stabilization. So let's say something like this. In this case, you could have a photon absorbed and an electron excited to a high shell. Let's say n is equal to 3 shell. But through resonance, the electron can relax down, not all the way to the ground state, but let's say from 3 to 2 through resonance stabilization. So let's say that we had n is equal to 1, n is equal to 2, n is equal to 3. So let's say we absorb a photon to bring an electron to the n is equal to 3 shell. And through resonance, the electron can relax down to n is equal to 2. Oh, and then let's say the energy from so let's say this is 1 electron volt, and then this is 0.5 electron volts. So this can absorb a photon with 1.5 electron volts, right?
Yes.
Moving an electron here. But then the thing is that it can relax down to n is equal to 2 through resonance. But then from n is equal to 2, it can go back down to n is equal to 1 through the usual means of emitting a photon, except this time the emitted photon would have what energy?
1 EV?
Yep. And so that's fluorescence. So in fluorescence, the energy of the photon absorbed is greater than the energy of the photon emitted. And this only works with molecules with extensive conjugation. So if you look up like the molecular structure of a dye or a pigment, like melanin, like in our skin, that's why, like, you know, we're not like getting
Burn.
yeah, yeah. and or like skin cancer and stuff, right? And that also coincides with the spectroscopic technique of UV vis, which detects conjugation, because it's like you shoot UV light at it, which it absorbs, but stabilizes through resonance and then emits so it absorbs the high energy UV and it
Yes.
emits a low energy visible light. And that's basically fluorescence. So yeah, these concepts, make sure you have it down because they're super, super high yield. You're guaranteed to see it on your test.
Okay.
And it's like not the most intuitive because, whenever I ask people this, it's like, what? But
I was like, what do you mean? But like, so say it's like still two, if there's two photons with one EV, it will still be in and it will still go from n equals 1 to n equals 2 shell. Like it won't, um,
yeah, they won't add up like that. Yep.
okay. But I guess like, would it excite more electrons if there was two, like
That's
one?
that's a good question, actually. Yep, yep. It would. So like let's say like one photon here will excite, and also like it would have to be, I mean, you would have to start with more than one atom. Like if you have one atom
Hmm.
and one photon, it'll get absorbed. But if you have one atom and two photons, like it'll still just go up to n is equal to 2. So,
Okay.
so the first photon will get absorbed, the other one just won't. But if you have more than one atom, then you could say more than one electron can get excited. But but yeah, so basically this and then fluorescence, and then the last thing's like the photoelectric effect, but that would be like, what if we had a photon with 2 electron volts? So that means that, and since the highest energy level here is 1.5 electron volts. So if it's 2 electron volts, the electron will be not just excited, but ejected. And that's when it actually leaves the atom.
Gotcha.
And so the photoelectric effect has a formula like this, where we have the energy of the photon, and then this is the work function, which is a way of saying like the ionization energy, aka the energy required to remove a photon. Sorry, to remove an electron. And so basically, if we plugged in 2 electron volts for the energy of the photon and then 1.5 for the work function, we still get zero point 0.5 electron volts, and that's the kinetic energy of the electron,
Okay.
right? So these are the three scenarios for essentially like quantum mechanics. So so example one involves the energy of the photon absorbed must equal the energy of the gap between the shells of the
Okay.
electron. And so the energy of that gap is equal to the energy of the photon absorbed, which is also equal to the energy of the photon emitted. So that's example one. Example two, if you have a molecule with conjugation, the energy of the photon absorbed will be larger than the energy of the photon emitted, and that's fluorescence. And then lastly, scenario three, if the energy of the photon exceeds the highest energy shell of the atom, then that electron will not just be excited, but it'll be unbound and ejected and leave the atom with some velocity. So, so that also means that in the first two examples, where you just have excitation, you're not changing, like the atom still has the electron, right?
Yes.
But in the photoelectric effect, the atom loses the electron, so the atom then turns into an ion, right?
Yeah.
Yeah.
And then like they would, so I guess that's how you would find the velocity, like just setting it equal to the kinetic energy.
Uh, so like this will help you get the kinetic energy of that electron.
Yeah.
Finding its velocity is not going to be easy because, I mean, theoretically, you could set it equal to 1/2 mv squared, right?
Yeah.
But the mass of an electron is like negligible. So, and also when you get to that scale, like with quantum mechanics, like you like there's like something called the Heisenberg uncertainty principle where like on that scale, you can't so like for macroscopic things, if you know like let's say the speed of something or the acceleration it experiences or the force it experiences, you can predict its final velocity and all sorts of stuff, but in quantum world, like the quantum world, you can't. So the Heisenberg uncertainty principle basically states that the more you know about the position of an electron, the less you know about its velocity and vice versa. So that,
Oh,
yeah.
yeah, I remember that one. Okay, now it makes sense. I was just kind of like, okay, like know that, but okay, that makes sense.
Yeah. So like you know how like an electron orbital could like look like this?
Hmm.
So what that really means is it like and so like also that means that it's not like the way that I drew it here where the electrons are like in orbit around, the nucleus, like that's not really like, how it looks like. It looks more like an orbital like this, which is just a probability density, which means essentially that the electron can be anywhere in here. So like let the dots I'm gonna make would be so like let's just say so the electron is here and then it's here, then it's here, and then it's here. And you can't see it move from here to here. It's pretty much like it's teleporting. And it can teleport anywhere in this probability cloud. And it's impossible to predict. Like if you had a regular object that's here at 1 second and then here at 2 seconds, we could say that it moved this way. But if you have an electron here and then here, you can't say that it moved from here to here. It's impossible. So, so yeah, so you wouldn't actually be able to calculate the speed of the ejected electron. Um, you could calculate its kinetic energy, but when you try to do this, yeah, it gets you can't really do that.
Okay.
Mhm.
So I guess that for this question, I would just use the H equals F times E and get the
Try that again.
wait. Yeah. Wait, no, I'm bugging. Yeah. It's E.
Mhm.
F. Yeah. Okay, my
Yeah.
bad.
So now the reason I went through all of that was because, like, sure, this answer happens to be just equal to, like energy of the photon is equal to Planck's constant times frequency. But what they're asking is the gap between the energy levels, and that's basically this gap, right?
Right. So
Hmm.
would it, I'm just a little confused. So it's like so that would be like 1 eV. Is that equal to joules as well, or
Oh,
does
so in the examples I was using 1 EV as just an easy number.
Mhm.
But the reason that I talked about with that was that like so this is essentially like if this is 1 electron volt and the photon causes this electron to be excited, the photon must have energy of 1 electron volt.
Right.
So so here, like what they're asking isn't exactly, they're not really asking what's the energy of the photon. They're asking what is the energy of this gap, which would equal the energy of the photon if that photon got absorbed.
Okay. That okay. 'Cause it's like all
Yeah.
yeah. It's like discrete. Oh well.
Yep, yep. So yeah, this question like coincidentally could be solved by using that formula, but that happens to be the answer because that happens to be the gap between the atomic energy levels.
Okay.
Mhm.
Gotcha. Cool. So, okay, let me see what it is. Oh, 6, 9, 10, 15. Is it wait, hold on. I don't know. Is it this one? I'm like, did I do my math wrong?
So you did this times this, right?
Yeah.
Now I could show you
Oh,
like you could round and stuff, but I could show you like the way that I would do it,
okay.
which is, well, how do you think I would do it?
So I mean, like what I did, I just added the exponents together first, and then I multiplied the 6.6 times 1.5, but I always just multiply it as 66 times 15, and then I add in the two decimals.
Yeah, so I would say you could round to make it easier. So like if you made this a 7 and if you round this, so like let's say we rounded the 6.6 up to a 7, we could round this one down.
Okay.
But what I would do that I never see anyone else do is like I always like fractions better because that way I don't have to approximate. So 1.5 is 3 over 2. 2
Yeah,
goes into 6.6 3.3 times. 3 times 3.3 is 9.9. And then I don't have to round.
that's quicker too. So I feel like sometimes I do it that way, but it's definitely not all the time.
Yeah, it's funny because like yeah, ever since I was young, like I always did like math in ways that like I just never saw anyone else do. Um, but But yeah, that's the so yeah, like also yeah, the best move that you did was like the 17 plus the negative 34 because then you can get the exponent value. So yep, good job.
Yeah. Okay, cool. I feel like I always like try to stay away from that because I think sometimes they'll change up like the units sometimes.
Yeah,
Like,
yeah, because if you did the like okay, the 1.5 times the 3.3, you could just think of them as one digit numbers. So your that first number is going to be one digit also. But if it was like a two-digit number, then that exponent will have to change.
yeah.
Um, yep. Oh yeah, and then this is asking for, so what did I say? The number of electrons? Oh wait. All right. They're talking about electrons. So which will be related to photons, I guess, but Anyway, yeah.
Um, so yeah, yeah, I was confused by this one as well. I was trying to figure out how to get from because I see they gave us the electric current as 15 microamps. And I was thinking to divide like um 1.6 coulombs by the 15 microamps, but I don't think that's correct. Uh
So let's do our thing here. So you said so 15 times 10 to the negative 6. What can I write here?
amps.
What else could I like?
Oh, coulombs per second.
And then I can do 1.6 times 10 to the negative 19 coulombs in one electron, right?
Yes. Okay.
And then I would get an answer with what units?
Electron units per second.
Yep. And then that would be the number of electrons per second, right?
Yeah. Okay. Okay, that makes more sense because like I don't know. I started using ChatGPT to help me, LOL, and it gave me like another equation for amps, and I was just confused. I was like, what? Like I don't know.
Yeah. So when it comes to dimensional analysis, just always think about it like if you're confused about like, okay, do I multiply, do I divide? Like it'll be whatever gets you your whatever makes it so that the units you don't want cancel out and the units you do want stay in. And so that's why when you were reading this and you said, the microamps, I was like, okay, what's that? And then you said coulombs per second. So it's more useful to think of it as coulombs per second rather than just amps, because amps is just like what? It's just like a word, right? But coulombs per second, you get to see that it's a rate at which electricity, like electric charge, is passing through per second. Um, so yeah, it's just dimensional analysis.
Okay, so yeah, I guess I was just doing it backwards. So yeah, 15. So you just divide it.
Mhm.
For this one, I guess I'll round up to 2.
Yeah.
It's 15. Okay. Oh yeah, so I guess it's C. Well, I got 7.5 times 10 to the 13th.
Okay.
Like I think that's right, right? I feel like
Wait,
that's
wait, wait. So you said you got something times 10 to the 13, right?
yeah.
So now, so you said something like, let's say you got 7 times 10 to the 13, right? So we have something with 7 here and something with 10 to the 13 here, but what's the more important
Uh,
value?
the exponent.
Yep.
Yeah, gotcha.
Yeah.
Okay. All right. That makes sense. Yeah, this was the I n equals I over E. I was confused by that, but I guess I could just use dimensional analysis.
Yeah, so I is just current,
Hmm.
like V equals IR.
Yeah.
And then N is like the number of electrons. Um, but yeah, I knew they were gonna ask something about calcium here.
Yeah, I know my periodic table now. So
Hmm.
cool. And I just knew it wasn't any of the others, so I just put photoelectric effects.
And that's the last thing that I went over in scenario three, right?
Mm-hmm.
The kinetic energy of the electron is equal to the energy of the photon minus the work function.
Yes.
So yeah, those three things, like make sure you have that completely down because it's 100 trillion% going to be on the test and you can like foresee it. So, and also, and know what these other things are. So mass energy conversions, literally, it's like the or equals mc squared. Doppler effect, if the source of a wave, it could be a sound wave, it could be a light wave, is getting closer to you, closer to the observer, the observed frequency gets higher, moving away from the observer, observed frequency gets lower. What about the Venturi effect?
That is going from like I guess like a higher area to a lower area.
You're thinking of
And
the continuity equation?
okay, never mind. This one is pressure.
Okay, tell me about it.
Um this is basically how I guess like pressure um remains constant.
If I blow this way, what direction do you think this will move?
I don't think it'll move.
All right, let's say it does. Which direction do you think it'll move? Will it go up or down?
Down.
Wait, hold on. Not working. It usually works though.
Okay.
There we go.
Oh, cool. Yeah. Okay, so
Up, right?
yeah.
See?
Mm-hmm.
So, what's up with that?
Um,
So this is like the paper, and I'm blowing in this direction. I imagine like the air molecules here being moved here, which means they're no longer here, which means there's like a temporary vacuum here, which sucks this up into that. Oh,
okay.
and then also that's like how a straw works. Like let's say this is a straw with a liquid here. Like when you suck inwards here, you create a vacuum which sucks the liquid up into it. And this is also how a plane like with lift works. So basically a wing is designed so that the velocity of air is com so the velocity of the air above the wing is high and below the wing is low. And from Bernoulli's equation, you know where you have the pressure, oops, velocity term, oops, um, gravitational potential energy terms. So like let's say the height is kept constant. It
Mhm.
means if we have an increase in velocity, and this is equal to a constant, if we have an increase in the velocity, we must have a decrease in the pressure. So what happens here is above the wing, the air is moving with a higher velocity, which means it'll have a low pressure. And below the wing, you'll have a lower velocity, but a higher pressure. And that's how lift uh, happens, which can cause something, to fly. And also when like a hurricane like blows, breaks windows and stuff, the glass shards don't get blown into like the house. They get blown out and sucked by the fast winds uh outside of the house.
Okay.
So basically what the Venturi effect is the inverse relationship between the velocity of a fluid, and fluid includes like, gases as well, but like, moving. So the faster the fluid moves, the lower the pressure will be, and vice versa. What's
That's
up?
great because of the vacuum that's created.
Say that again.
Because you were talking about like how like when you were blowing on the paper,
Hmm.
because of how high the speed was, it created like a vacuum like
Yep.
over
Yep.
like with the Venturi effect that is also because of a vacuum as well.
Yeah, so that's basically the paper example was literally just the Venturi effect.
Hmm.
So right now, like just imagine air. It's just air. So things are the way they are. But if I blow the air this way, imagine the air particles that were here are now here and therefore not here. So this area is like a temporary vacuum, which is like a low pressure. So this gets sucked upwards towards that low pressure.
Okay, that makes sense. So it would be like the higher, yeah, inverse relationship. So the higher the velocity, the lower the pressure.
Yep. And
Is
then,
there
yeah.
for the Venturi effect? Like I don't know. Well, actually,
Wait, what's up?
is there an equation for the Venturi effect?
Oh yeah, so Bernoulli's equation is just conservation of energy applied on to a volume.
Mm-hmm.
And so there's a pressure term, there's a kinetic energy or velocity term, and there's a gravitational potential energy term. Now, you would have to have like the height be the same. So like here, let me draw like something like, oops, like this. So let's say this is point A and this is point B. So like we have three components in this equation, and in order to like we can't if we don't know the three of these, then we can't really solve. Like in an equation, you need to have one like unknown. So you would have to have so like in this where I drew A and B, I'm drawing them so that they have the same height, just so I can get the height part of this Bernoulli's equation out of the way.
Okay. I was confused because I was like it looked like they didn't have the same height, but like when you say height, do you mean like where it is in the center? Like here?
Yeah.
Okay, that makes sense. That makes sense.
Like if I had something like this and I'm comparing like A and B here,
Yeah, that
it's changing. So like the continuity equation would relate. So that's when you have like AB like that. I mean, you
Mhm.
can also see it equal to Q, but basically the idea is that Q or K is a constant, and the constant means that if area goes up, velocity goes down. If area goes down, velocity goes up. So we can see that in both of these examples, B, location B, has a lower area, therefore higher velocity, right?
Yeah.
But in this example, since they have a different height, I can't conclude uh, that pressure and velocity will be inversely proportional because there's a third, variable. So I can't do it for this. But here, let's say that, the dot or like the circle here is point A and point B. They have the same height. So now I can get this out of the equation, literally. So now I know that. So since V, so velocity at V, sorry, at B is greater than velocity at A, right? Because of the smaller area.
Yes.
And then so this equation here, since they have the same height, I don't care about this. But now I just have a pressure term and a velocity term. So if the velocity term goes up, the pressure term must go down.
Okay. All right. That makes sense. I mean, I kind of like, I just knew that the Venturi effect was like for fluids. So I was like, it doesn't have anything to do with this. But it's good that I understand it now.
Yeah, yeah. Like having a tendency towards over inclusion is a good thing to have, like just in general. Um, so yeah, you don't want to think like, okay, like if we're talking about fluids, then I'll start to think about the Venturi effect. If I'm talking about whatever, then I'll think about that. Like, especially when it comes to physics, because it's like it's happening always, like everywhere, around you. So you could even observe, like, if you turn on your faucet and you observe, like, the water that falls out of it, like, it's thicker right where it comes out of the faucet. But as it gets lower, you can observe that it gets thinner.
Yeah.
And that's like, this relationship.
The continuity equation.
Mhm. Yeah. So, but yeah, these like concepts, know them like, inside and out. Um,
Yeah, I just got down the Doppler effect. I feel like I understand it conceptually now. I'm just like I need to like memorize like the equations.
yeah, so the equation, like, sure. But yeah, just the conceptually is the most important part. So like, let's say that you use a telescope to look at a planet, and the planet is supposed to be green, but when you look at it, it looks a bit redder than it should look.
Yes.
So now, so Roy G. Biv. So like, okay, let's say so it's supposed to be green, but it appears red. So its wavelength is your observed wavelength is longer, which means the observed frequency is smaller or higher.
Smaller.
So that means that this is moving away from us, right?
Mm-hmm.
Through the Doppler effect. And that's how we know that the universe is expanding. It's called redshift. So just, like when people think of the Doppler effect, they think of sound, but it can happen with light as well. So yeah, just having a really, really, really like good foundational understanding of these concepts is going to be the most important thing. Yep.
Gotcha.
Mhm.
Okay, this had me tripped up. It was like, what is the effect of temperature increase on the dimensions of the openings through which the X-rays for the CT scan can pass? Um, so I think yeah, you were talking about it before now because you were talking about diffraction with like the with D, and you were saying that well, actually, I don't know if it like D is bigger than the wavelength, so I actually don't know if it would have to like squeeze through.
Yeah, so now
So.
this is actually I wasn't expecting them to ask us this. So this is actually talking about something a little bit different, but it's not like it's not like it's um like it'll still make sense. So basically, um if you increase the temperature of something, it can cause something to expand. Like you know why have you ever wondered well probably not, but have you ever well so like a sidewalk
Hmm.
has like gaps between them.
Yeah.
Why do you think?
Yeah, I think may probably because the Earth is moving. Maybe
So?
I don't know. I feel like it. It's like don't step on the crack or.
But like that, but like why? So like if it's bad to step on the cracks that make breaks your mother's back, why do they make them? Why don't they just make one continuous? So when it gets hotter, things expand.
Hmm.
So when it gets hotter, this can expand outwards and it won't crack it. You're essentially giving the gap, giving their like you're essentially creating a gap so that when the weather gets hot, that piece of the sidewalk can expand and it has room to expand into.
Okay, that makes sense. Well, I feel like they still don't have that much room, but it's okay.
Yep. But it's like they're not going to expand like, like eight, it's not going to make like a new, it's not going to be like that.
Yeah.
Because it's really it's expanding uh like like on a microscopic scale
Mm.
um but yeah so basically thermal expansion is something that can happen um well to like liquids and solids but like it's true for gas like a gas if the temperature goes up the volume goes up right
Yes.
so and that can happen with like liquids and solids as well.
Hmm.
And yeah, so that's pretty much. So yeah, so this question is so it's asking us what would happen to either the slit distance or and the length of like the entire thing. Like let's say this is the length and then this is the slit and this is the width of the slit, which is D. And so if you heated this up, the length would increase.
Yes.
And now the thing is, so I'm going to draw it bigger here. So now the thing is that the length of this like would increase, which would actually make the gap smaller, right?
Wait. You mean like the length of like the length of like this part?
Yeah, so like yeah, so basically the thermal expansion will happen to like the solid object. So the solid object will become longer.
Yeah.
And since the gap is just, the region where the solid is not, when the solid expands, it'll make that gap get smaller. It's like the gaps between the sidewalk tiles or whatever. Like when these tiles expand, they expand into that region where there's a gap, and that must mean that the gap gets smaller, right?
Yes. Okay. That
So this is actually an interesting question because the length L here is actually the length of the, whatever, the compartment, but the D, the width, is the opening. So it's not the length or width of any physical object, but, the gap between the two.
okay.
Mhm.
All right. That it's like what concept is that? Just physics?
So the concept is, yeah, physics with expansion. There's a linear expansion, there's a volumetric expansion. Um there was actually one in the beginning of this section bank where they asked you where they talk about the AIOL thing with the I.
Yeah.
And they're like, this can only increase by this much. And then you had to figure out volumetrically like how much it expands. Like it's essentially like I think it's like let's say alpha times original length is the um new length. So so if I have a length, let's just say this is like 1 meter, and I heat it up, it's gonna expand to be greater than 1 meter, right?
Yeah.
And so this is a linear expansion in one dimension. But if we're talking about an area, which is in 2 dimensions, you would then have to multiply it by 2 times this linear expansion. And then if we're talking about a 3-dimensional volume, it would be 3 times this linear expansion. So, um, okay, so that's the concept, the physics concept. So that's why L is going to increase. But the thing with D, it isn't just that L is increasing more than D. It's that L is increasing and D is decreasing because D is the gap rather than the actual solid material. So this is essentially asking like if you have two tiles with a gap in between, and let's say this is the L, the length of the tile, and then this is D, the gap between tiles. If you increase the temperature, what would happen? Well, L would increase, and what would happen to the gap?
No, it would decrease.
Yep.
So, okay.
No,
Um,
so you said L would increase,
yeah.
and the gap D would.
Uh, decrease.
Yeah. So which choice says that?
Is it not this one? Or
Oh, I
maybe.
see what you're saying. So this says that L increases by the same amount that D decreases. So, we can't say that, right?
Oh, because we don't know how much they're increasing or what.
Yeah. So, like, yeah, because this is saying too much. But this one, I guess, would fit.
Okay. Yeah, because I think I put C before, so yeah, maybe I was just going for
Hmm.
too descriptive.
Oh yeah, so there's a delta T term in there.
Oh,
But yeah, cool.
okay. Um, okay, this is where the grays come in, where it was like, what is the minimum radiation energy absorbed in 2 seconds by 20 grams of heart tissue that is associated with the formation of plaques?
Okay.
So, it says here the unit of 1 gray represents 1 joule of radiation energy absorbed by 1 kilogram. So I thought it would be, I was like, okay, I'll change the 20 grams to kilograms. Just,
Hmm.
and then I was like, I guess I multiply by 0.04.
So let's set it up, right? So for instance, um, let's see. So we have 0.04 GY over seconds, which is 1 joule per kilogram. So on the bottom, since I have the GY thing on the top, and I want to get rid of it for our answer, on the bottom, I'm going to put that unit, that same unit. So 1 GY, and then they say that's equal to 1 joule per kilogram. So I could say up here, like 1 joule per kilogram. It's kind of messy. I'm gonna do it like this instead. I'm gonna do 1 GY. Let's see. 1 GY. Well, you know what? I could just since it's equal to a joule per kilogram, I'm just gonna write joule per kilogram, and then I can do the 0.02, or I might as well just do 20 E negative 3 kilograms, so I can cancel out the kilograms part. And then they said that this is that many GYs per second. So that would then be 0.04 joules per second, which means I could put the seconds up here.
Times 2. Wait,
Yeah.
so it's,
Uh,
wait,
tell me what you were gonna do.
um, what I was gonna do,
So I that seconds term was messing with the way that I was setting it up. So I'm gonna get rid of it by just straight up multiplying this by 2 seconds to get 0.08 GY.
oh, okay. I think that's a good way to do it. I was confused about the seconds term too. I didn't know what to do with that. I divided by the seconds just because I was like, I guess.
Yeah. I was like, this is cramping my style. Let's get rid of it. So okay, we got rid of it. So we have this, and we know that this is equal to a joule per kilogram. So 1 joule, 1 kilogram, and then
Times the 20 times 10 to the negative third kilograms. Oh, wait, that's on the bottom. Wait. Oh, okay.
yeah, okay, I'm gonna make it so it's not on the bottom. So this. Wait. Raise. Okay. So this is what I'm going to do. So I'm going to just okay, so we know that 0.08 GY in 2 seconds, right?
Yeah.
And if one GY is 1 joule per 1 kilogram,
Hmm.
I could write this as 0.08 joules per kilogram, right?
Yes.
And then I can multiply it by 20 e negative 3 kilograms. So I'm going to take the 0.08 and I'm going to actually turn it into 8 e negative 2 joules per kilogram times 20 e negative 3 kilograms. And I could just do 20 times 8, which is, I guess, 160 e negative 5. And I guess that'll be that
Cool.
one.
Yeah.
So
Okay.
that was a
Good.
bit tricky. Um, so we had to be yeah. That was not as straightforward of a dimensional analysis problem as they usually are. So I had to do some other stuff. Like I had to take the 0.04 GY per second, get rid of the seconds to get zero point zero 0.08, and then get rid of the GY. And since GY is equal to, joule over kilograms, it wasn't as simple as a usual dimensional analysis because usually a dimensional analysis is one term is equal to another term rather than one term is equal to some other term divided by another term.
Hmm.
So yeah, that was a bit tricky.
It's silly. I mean, not tricky, but I mean, no, whatever. We got through it. I
Mhm.
feel like I need to remember like if I see I guess like a unit that is tripping me up, I should try and figure out how to get rid of it. Like I
Hmm.
didn't think to do to just like get rid of the seconds earlier,
Hmm.
but yeah, I feel
Yeah,
like that I could use moving
yeah,
forward.
yeah.
Um, I thought that it would be diamagnetic because calcium has is like 2 plus.
Um, let's see. So diamagnetic would mean that diamagnetic would mean that it does not have an induced magnetic field, right?
Okay.
Because I think that so if you had like if it was paramagnetic, I think that it would be responsive, but okay, diamagnetic would have paired electrons, paramagnetic would have unpaired electrons, and calcium.
Calcium has unpaired electrons.
Mm-hmm. Okay. Can you open up the periodic table? Let me take a look. Calcium. So this is 4s2. If it gained an electron, it would be in the 3d region. So let's see. Now, okay, so I'm pretty sure diamagnetic would have your paired electrons, so they're not going to be making a magnetic field. But since they're telling us in the passage that the calcium um, was able to, oh, okay. So they irradiated it, right, by shooting X-rays at it, and that would cause an electron to be excited to a
Yeah.
higher energy shell. And even though this is 4s and this is 3D, the 3D orbital is a higher energy shell, right?
Wait,
Hmm.
this is the D right here.
Hmm.
Okay.
Yeah. And it's higher in energy than the S ones.
Really?
Mhm.
Okay. I guess I'm confused because I'm like when I was looking, like when I was like writing down like the like I guess like the electron configuration for zinc, they were like, oh, zinc would lose energy from the 4s like it would lose electrons from the 4s orbital first. Or is it?
So if you wrote the electron configuration for zinc, right, it would be like argon and then 4s2 3d10, right?
Yeah.
And so we fill the 4s before we fill the 3d.
Yes.
Just like anything else, we fill the like like 1s 1 for hydrogen, 1s2 for helium, and then for lithium, it's 1s2, 2s1, right?
Mm-hmm.
So we increase energy as we increase, from 1 to 2 to 3, but we also increase energy once we get to the p orbitals here,
Yes.
right? And then here, like after this, we fill these d orbitals, right?
Okay.
So since we fill the 4s orbitals before the 3d orbitals, right? Like for zinc, this would be it, right? It's
Yeah.
not like we do like 3d10 and then 4s2, right?
Yeah.
So so the 3d orbital is um filled in, well, the 3d orbital therefore mean must be at a higher energy level. And if the calcium is being irradiated, like it's what I was kind of drawing right in the beginning, like you shoot photons at it and it causes an electron to be excited to a higher energy shell. So you
Mm-hmm.
have an electron from the 4s orbital get excited and jump up to the 3d orbital to get 4s1, 3d1.
Okay.
Mhm. So so this would be paramagnetic. And it was very, very tricky because I was thinking of what about when calcium loses electrons to be like, calcium 2 plus.
Yeah, that's what I was
But,
thinking.
but since they're saying neutral, that means that it's not being ionized. But
Oh,
um, you can have an electron get excited without that electron leaving the atom, right? Like in what we were talking about with photons being absorbed. So here
Yeah.
they're shooting the X-rays at the calcium, which then produces its electric field. So we know that this is going so basically calcium is producing an electric field, which means sorry, a magnetic field. Magnetic field. Calcium is producing a magnetic field. And if it's diamagnetic, it means it's not producing its magnetic field. And so then the question is, how would calcium, something that's diamagnetic, produce a magnetic field? Well, if an electron is excited to its a higher energy shell, like the 3D shell.
Okay.
Hmm.
Tricky, but
Yeah, yeah. The section bank too is super not straightforward. Um, but yeah, pretty much.
okay. Well, I'll keep working through it, but like, are you saying I should work through section bank one first and then come to section bank two, or
You can do it in whichever order. Um, yeah, you can do it whichever order you want. Section bank one is more straightforward. Like, this is like a lot less straightforward, but yeah, whatever order you do it doesn't matter, but they're both very important, so I would just make sure to get both of them done.
okay.
Um, and And yeah, make sure you know those things about the photons and all of those examples and practice more dimensional analysis stuff. If you actually go to jackweston .com, you can open that up and um yeah.
Oh, okay.
Mhm. Yeah, and then scroll down. Yep, keep going. So now first yeah, hit the where it says sections up there.
Where?
Um, okay, right, yeah. Now scroll down. I think it'll be fundamental. Yeah, keep going. Let's see. I think it'll. Yeah, try CP here.
I started listening to their podcast. Wait, did it not go through when I
Oh
clicked?
yeah, here it is. Yeah. So see these physical discretes. Like you could just click on one or any of them. So these are like yeah. Look through the questions. Yeah, so these types of problems are like just like all like some of them aren't math, but like most of them are like math and dimensional analysis calculation problems. So yeah, I would say to do like a bunch of these and get really good with practicing dimensional analysis. That's something that like it's hard you can't like just like memorize it. You have to like actually practice and do it. So yeah, just I would say practice doing all these, yeah, as many as these dimensional analysis problems as you can. So you get really like nimble with it. Um, and and then like yeah, try to get through the section banks and then yeah, take your test and then we'll meet sometime next week to go over your full length as well as like some yeah, so let's meet like twice next week, like one like early in the week to go over stuff, questions from the full length and section banks and stuff, and then another session to go over like just last minute stuff before your test.
Okay. Should I do it the day before my test, or should I do it like Thursday maybe?
Do what?
The last minute go over things before my test.
Oh, when you say your test, you're saying the practice test?
No, the real test.
Oh,
Like next week. Because my test is on Saturday, so I was like, oh, should I like meet on Friday or should I do like Thursday? Like so I have like a day to
Hmm. Yeah, let's do Thursday. So let's
like,
see.
yeah, we'll do Monday and Thursday next week then.
All right. Do you want to do would 4:30 p.m. Eastern
Yeah.
work
On
on
Thursday and Monday.
Yep.
Yeah.
Okay. So putting you in for 4:30 Eastern on Monday the 23rd and 4:30 Eastern on Thursday the 26th.
Okay.
All right. Awesome. And then let's see for today. One, two. Should be 180
Okay.
for today. So, keep up the good work. Good luck on that last full length, and I will see you Monday and Thursday.
All right. Have a good
Awesome.
thank you.
You too. Take care.